Welcome back to the Midnight Vessel. The ship is moving tonight, slowly, steadily, cutting a straight line through dark water toward a sky that is not quite right. The stars are out, but they are not the only things up there. Around the galaxies visible overhead, faint halos of something shimmer at the edge of perception. Not light exactly, not darkness exactly, but the suggestion of a presence that the eye cannot focus on no matter how long it tries. The lanterns on either side of the deck cast their warm gold across the planks, and the ocean ahead is still, and the cosmos above is doing something that took humanity most of the 20th century to begin to understand. Most of the universe is missing. Not lost missing. Present, exerting force, shaping everything we can see and completely invisible. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a large collection of galaxies, roughly 320 million light-years from Earth. He measured the velocities of the individual galaxies within the cluster, then calculated how much mass the cluster would need to contain in order to hold those galaxies together gravitationally. The answer did not match. The galaxies were moving far too fast, fast enough that, based on the visible mass alone, they should have flown apart long ago. The cluster should not exist. And yet, there it was. Zwicky concluded that there must be additional mass in the cluster, that he could not see what he called, in German, dunkel Materie. Dark matter. The observation was largely ignored for the next 4 decades. The idea was revived, transformed, and made undeniable in the 1970s by an American astronomer named Vera Rubin. Rubin was studying the rotation curves of spiral galaxies, measuring how far stars at different distances from the galactic center were orbiting. According to Newtonian mechanics and the distribution of visible matter, stars further from the center should orbit more slowly, the way the outer planets of the solar system move more slowly than the inner ones. Instead, Rubin found that stars at the outer edges of galaxies were orbiting at roughly the same speed as stars near the center flat rotation curves, galaxy after galaxy, with no sign of the expected decline. The only explanation that fit the data was that each galaxy was embedded in a vast halo of invisible mass extending well beyond the visible disk of stars, providing the gravitational pull needed to keep the outer stars on their orbits. The stars we see are not the whole galaxy. They are the visible tip of something much larger. Rubin's findings were not immediately welcomed. The history of science is full of correct observations that were resisted because they implied something too strange, too disruptive, too costly to the existing picture. A universe in which most of the matter is invisible, in which the stars and planets and gas clouds that fill the night sky account for only a small fraction of what is actually there, was not a universe anyone had been prepared for. But the data kept coming in from different telescopes, different galaxies, different methods, all pointing to the same conclusion. By the 1980s, dark matter had moved from fringe hypothesis to mainstream consensus, not because anyone had seen it, but because the evidence for its gravitational effects had become impossible to ignore. The universe had been weighed, and it came up short by a factor of roughly 6. The numbers, worked out in increasing detail over the following decades, are staggering. Ordinary matter, the protons, neutrons, and electrons that make up everything we have ever touched or seen or measured directly, accounts for approximately 5% of the total energy content of the universe. Dark matter accounts for roughly 27%. The remaining 68% is something else entirely, a different mystery called dark energy, which we will come to in a later passage. In other words, the matter and energy that constitute the entire known universe, every star, every planet, every atom of every living thing is 5% of what is out there. The rest is dark. The rest is something we have never held in a hand, never detected in a laboratory, never observed directly in any way. And yet, without it, none of the 5% would exist in the form it does. The galaxies overhead are embedded in halos of it right now. The ship is moving through it, not that anything would feel different if the dark matter suddenly vanished, not that any instrument on the deck could register its presence. It passes through ordinary matter almost without interaction, a ghost of the cosmos that exerts gravity, but nothing else we have yet been able to measure. In the next passage, we look more carefully at what dark matter is not, at the long process of elimination that has narrowed the field of candidates and made the mystery sharper and stranger with every answer found. Science often advances by elimination, by ruling out what something is not, until what remains, however strange, must be the answer. Dark matter has been subjected to this process for decades, and the result is a portrait defined almost entirely by absence. It is not any of the things it was first suspected to be. It is not the ordinary matter we know, not gas clouds too diffuse to see, not burned out stars, not planets too small and cold to emit light. It is not black holes of the ordinary stellar variety. It is not neutrinos, those ghostly particles that pass through ordinary matter in enormous numbers, but whose mass is too small to account for the gravitational effects observed. The process of elimination has not yet produced an answer, but it has made the question much more precise. The first candidates to be seriously considered were ordinary objects that simply happened to be dark, what astronomers called MACOs, for massive astrophysical compact halo objects. Brown dwarfs too small to ignite nuclear fusion, ancient white dwarfs that had cooled to invisibility, rogue planets drifting through space with no star to orbit objects made of familiar matter, simply unlit. These were appealing candidates because they required no new physics, only the acknowledgement that not everything in the universe emits light. Surveys designed to detect MACOs, looking for the brief brightening of background stars caused by the gravitational lensing of a massive compact object passing in front of them, found some, but nowhere near enough. MACOs exist, but they account for only a small fraction of the missing mass. The halo cannot be made of ordinary dark objects. Something more exotic is required. Neutrinos were another early candidate. They are produced in enormous quantities by nuclear reactions in stars and by radioactive decay, and they pass through ordinary matter almost entirely without interaction. Billions of them are passing through your body every second as you read these words, leaving no trace. They have mass, however small, and they exist in vast numbers, which made them plausible contributors to the dark matter budget. The problem is that neutrinos move very fast, close to the speed of light, which makes them what cosmologists call hot dark matter. Computer simulations of a universe dominated by hot dark matter produce a large-scale structure that looks nothing like the universe we observe, too smooth, too uniform, without the filaments and clusters and voids that characterize the actual cosmos. Neutrinos contribute something to the mass budget, but they cannot be the dominant component. The dark matter must be cold, slow-moving, clumping together under gravity to form the structures we see. Primordial black holes formed not from collapsed stars, but from density fluctuations in the very early universe, enjoyed a period of serious consideration, particularly after the LIGO gravitational wave detectors began finding merging black holes heavier than expected from stellar evolution alone. If the early universe had produced black holes across a range of masses, they could be drifting through galactic halos, invisible and gravitationally significant. Detailed constraints from gravitational lensing surveys, from the cosmic microwave background, and from the distribution of gravitational wave detections have since ruled out primordial black holes as the dominant form of dark matter across most of the plausible mass range. They may exist, they may contribute, but they are almost certainly not the whole answer. What all the failed candidates have in common is that they are made of ordinary matter, the same protons, neutrons, and electrons that make up everything we can see and touch. The constraints from Big Bang nucleosynthesis, the process by which hydrogen and helium were forged in the first few minutes after the Big Bang, place strict limits on how much ordinary matter the universe can contain. Those limits are consistent with the 5% figure. If dark matter were made of ordinary matter, there would simply be too much of it, more than nucleosynthesis could have produced. This is one of the most powerful arguments that dark matter is something genuinely new, a form of matter that does not participate in the nuclear reactions of the early universe, that interacts with ordinary matter only through gravity, and that exists outside the catalogue of particles that the standard model of particle physics describes. It is not hidden ordinary matter. It is something else entirely. The process of elimination has been thorough, and the remaining candidates are strange. In the next passage, we look at the positive evidence, not what dark matter is, but the multiple independent lines of observation that have confirmed its presence so thoroughly that most physicists treat its existence as established fact, even in the absence of a single direct detection. The case for dark matter does not rest on a single observation. It rests on a convergence, multiple independent lines of evidence, developed by different groups of scientists using different instruments and different methods, all pointing to the same conclusion. This convergence is what separates dark matter from a hypothesis to something closer to an established fact. We have not detected a dark matter particle directly, but we have measured its gravitational effects so many times in so many different ways that the existence of something producing those effects is about as secure as any conclusion in modern science. The evidence is indirect, but indirect evidence, when it is this consistent, is still evidence. Gravitational lensing is one of the most visually striking demonstrations of dark matter's presence. Einstein's general relativity predicts that massive objects bend the path of light passing near them, and the more massive the object, the more the light is deflected. When a massive galaxy cluster lies between us and more distant galaxies, the cluster acts as a gravitational lens, bending and distorting the light from the background galaxies into arcs, rings, and multiple images. By measuring the degree of distortion, astronomers can calculate how much mass is doing the lensing, and the answer is consistently far more than the visible matter in the cluster can account for. The mass distribution inferred from the lensing extends well beyond the visible gas and stars, tracing the outline of a halo of dark matter that is not emitting any light but is nonetheless bending the fabric of space around it. Dark matter leaves its signature in light it never touches. The bullet cluster is the single most compelling piece of evidence for dark matter as a real physical substance rather than a modification of the laws of gravity. It is the aftermath of a collision between two galaxy clusters, a cosmic crash that occurred roughly 150 million years ago and is still visible in the sky today. When the two clusters pass through each other, the hot gas which makes up most of the ordinary matter in galaxy clusters slowed down due to electromagnetic interactions, piling up in the center of the collision like cars in a traffic accident. But the dark matter, which interacts with nothing but gravity, passed straight through, continuing on with the galaxies. X-ray observations show the hot gas concentrated in the middle. Gravitational lensing maps show the mass and therefore the dark matter separated from the gas displaced to either side. The mass went one way, the ordinary matter went another. That separation is very difficult to explain without a component of matter that does not interact electromagnetically. The cosmic microwave background, the faint glow of radiation left over from the early universe, about 380,000 years after the Big Bang, carries, in its temperature fluctuations, a precise record of the conditions at that early time. The pattern of these fluctuations depends sensitively on the composition of the universe, on the relative amounts of ordinary matter, dark matter, and radiation. Detailed measurements of the cosmic microwave background by the WMAP and Planck satellites have produced a precise census of the universe's contents: 5% ordinary matter, 27% dark matter, 68% dark energy. These numbers are entirely consistent with the dark matter inferred from galaxy rotation curves, from gravitational lensing, and from the large-scale structure of the universe. 3 completely independent methods. 3 consistent answers. Computer simulations of cosmic structure formation provide a 4th line of evidence. Starting from the tiny density fluctuations visible in the cosmic microwave background and running forward in time, simulations that include dark matter produce a universe that looks like the one we observe with galaxies arranged in filaments and sheets around vast empty voids, clustered in groups and superclusters, with a distribution of galaxy sizes and masses that matches observation. Simulations run without dark matter produce a universe that looks nothing like ours too smooth, without the hierarchical clustering that characterizes the actual cosmos. Dark matter is not just an explanation for what we see in individual galaxies. It is a necessary ingredient in the recipe for the universe as a whole. The evidence is overwhelming and the mystery is intact. Every line of observation confirms that something is there. Not one has told us what it is. In the next passage, we turn to the candidates, the theoretical particles that might constitute dark matter, the experiments searching for them, and the question of why, after decades of searching, none of them have yet been found. The leading candidate for dark matter for most of the past 4 decades has been a class of hypothetical particles called WIMPs, weakly interacting massive particles. The name describes their key properties. They have mass in the range of roughly 10 to 1,000 times the mass of a proton, and they interact with ordinary matter only through the weak nuclear force and gravity, not through electromagnetism, which is why they neither emit nor absorb light. WIMPs were appealing not just because they fit the observational constraints, but because they emerged naturally from theories of particle physics developed for entirely independent reasons. Supersymmetry, a theoretical extension of the Standard Model, predicted the existence of a stable, neutral, massive particle that would have been produced in the right quantities in the early universe to account for the observed dark matter density. The coincidence was striking enough to be called the WIMP miracle. For a while, it seemed like dark matter was waiting to be found just around the corner. The search for WIMPs has been one of the most extensive experimental programs in the history of physics. Deep underground laboratories, shielded from the cosmic ray background by kilometers of rockhouse detectors of increasing sensitivity, cooled to near absolute zero, waiting for the rare occasion when a WIMP might scatter off an atomic nucleus and deposit a tiny amount of energy. The Large Hadron Collider at CERN has searched for WIMPs produced in high-energy proton collisions. Space-based experiments have looked for gamma rays that WIMPs would produce when they annihilate each other in regions of high dark matter density. None of these searches has found a confirmed signal. The detectors have grown more sensitive by orders of magnitude. The limits on WIMP properties have become extraordinarily tight. And the silence has continued. The non-detection of WIMPs has broadened the search considerably. Axions, are another leading candidate, much lighter than WIMPs, originally proposed to solve a different problem in particle physics entirely, but possessing properties that make them viable dark matter candidates. Detecting them requires experiments involving strong magnetic fields and resonant microwave cavities, searching for the faint conversion of axions into photons. Sterile neutrinos, hypothetical cousins of the known neutrinos, with no weak force interactions at all, are another possibility, suggested by anomalies in X-ray observations of galaxy clusters. The field has expanded from one strong candidate to a landscape of possibilities, each requiring different experiments, different techniques, different conceptual frameworks. There is a third possibility that cannot be dismissed, that dark matter does not exist as a particle at all, and that what we observe is instead a failure of our theories of gravity at the scales of galaxies and clusters. Modified Newtonian dynamics, or MOND, adjusts the law of gravity at very low accelerations in a way that reproduces many observed galaxy rotation curves without invoking additional matter. For individual galaxies, MOND works remarkably well. For galaxy clusters, for the cosmic microwave background, and for the large-scale structure of the universe, it struggles badly. Modified gravity remains a minority view, but a scientifically serious one. The question of what dark matter is cannot yet be separated entirely from the question of whether our theory of gravity is correct at all scales. The experiments continue. The Xenont detector in the Gran Sasso laboratory in Italy, a tank of 10 tons of liquid xenon buried under a mountain, is currently one of the most sensitive WIMP detectors ever built. The ADMX experiment in Washington State is scanning the mass range where axions are most theoretically motivated. The Vera Rubin Observatory, named for the astronomer whose rotation curves made dark matter undeniable, is mapping galaxies across an enormous volume of the universe, looking for statistical signatures of dark matter's influence on structure formation. Every null result tightens the constraints. Every tightened constraint changes what is possible. The search has not found dark matter, but it has learned an enormous amount about where dark matter is not hiding. The ship moves through the dark water, and the galaxies overhead hold their halos of invisible mass, and the experiments deep underground continue their patient vigil, listening for a signal that has not yet come. In the next passage, we turn to the other great mystery, hiding in the darkness, dark energy, the force that is not only invisible, but is actively pushing the universe apart, accelerating its expansion toward a future we are only beginning to understand. In 1998, 2 independent teams of astronomers were measuring the distances to Type Ia supernovae stellar explosions of known brightness that serve as standard candles across the cosmos, allowing precise measurements of how fast distant galaxies are moving away from us. Both teams expected to find that the expansion of the universe was slowing down, decelerating under the gravitational pull of all the matter within it, the way a ball thrown upwards slows as it rises. Instead, both found the opposite. Distant supernovae were dimmer than expected, further away than they should have been, if the expansion were decelerating. The universe was not slowing down, it was speeding up. The expansion of the universe is accelerating, driven by something that could not be identified, could not be observed directly, and had no theoretical framework to explain it. They called it dark energy. Dark energy is not the same as dark matter, and the two should not be confused, despite sharing the word dark. Dark matter is a substance, something with mass, that clumps under gravity and holds galaxies together, present since the earliest moments of cosmic history. Dark energy is something fundamentally different, a property of space itself, uniformly distributed throughout the universe, not clumping, not diluting as the universe expands, exerting a negative pressure that causes space to expand at an accelerating rate. Where dark matter pulls things together, dark energy pushes everything apart. Where dark matter is concentrated in galaxies and clusters, dark energy is everywhere equally, in the emptiest void and in the densest cluster alike. They are opposite forces, operating on opposite scales, and together they account for 95% of the universe. The simplest theoretical description of dark energy is Einstein's cosmological constant, a term he originally introduced into his equations of general relativity to produce a static universe, then removed when Hubble's discovery of cosmic expansion made a static universe untenable. Einstein called the cosmological constant his greatest blunder. It turns out the blunder was removing it. The cosmological constant can be interpreted as the energy density of empty space, vacuum energy, a consequence of quantum mechanics, whereby the vacuum seethes with virtual particles continuously popping in and out of existence. The problem is that when physicists calculate how large the vacuum energy should be, they get a number somewhere between 50 and 120 orders of magnitude larger than the observed value. This is sometimes called the worst prediction in the history of physics. Something is cancelling the vacuum energy down to nearly zero, but not quite zero, and no one knows what. Alternative explanations for dark energy have been proposed and studied. Quintessence is a hypothetical dynamical field whose energy density changes slowly over cosmic time, mimicking a cosmological constant now, but with subtly different predictions for the future. Modified gravity theories attempt to explain the acceleration without any additional energy component at all. None has been definitively confirmed or ruled out. The Dark Energy Spectroscopic Instrument and the Euclid satellite are currently mapping hundreds of millions of galaxies across cosmic time, looking for subtle variations in the expansion history that would distinguish a true cosmological constant from a dynamical field. The results will not resolve the mystery immediately, but they will tighten the boundaries of the unknown considerably. If dark energy continues at its current value, the long-term future of the universe is one of increasing isolation. Galaxies beyond our local group are already receding faster than light, not because they move through space at superluminal speeds, but because the space between us and them is expanding faster than light can cross it. In the far future, those galaxies will redshift beyond detectability and eventually vanish from our observable universe entirely, not because they are destroyed, but because space between us has stretched to the point where no signal can bridge the gap. Civilizations arising in the far future may look out at a universe that appears to contain only their own galaxy, with no evidence that the vast cosmic web we can see today ever existed. Dark energy will erase the evidence of its own context. In the next passage, we look at the structure. Dark energy is gradually taking apart the cosmic web, the largest pattern in the universe, built by dark matter across billions of years. If you could step back far enough, not just outside the solar system or the galaxy, but far enough to see the universe as a whole, what you would see is not a uniform scattering of galaxies spread evenly through space. You would see a structure, a vast three-dimensional web of filaments and sheets, with galaxies clustered along the threads and at the intersections, and between them enormous empty voids, hundreds of millions of light years across, containing almost nothing at all. This is the cosmic web, the largest structure in the universe, a pattern that extends across billions of light years and contains every galaxy that has ever formed. It was not designed, it was not placed there. It grew over billions of years from the gravitational influence of dark matter acting on the tiny density fluctuations left over from the Big Bang. The process began in the first fraction of a second after the Big Bang, when quantum fluctuations in the density of the early universe were stretched to cosmic scales by a period of extraordinarily rapid expansion called inflation. These fluctuations left some regions of the universe very slightly denser than others, density contrasts of roughly 1 part in 100,000, barely above the noise of thermal radiation. In an ordinary matter universe, these tiny overdensities would have struggled to grow. The pressure of the hot radiation-dominated plasma would have resisted gravitational collapse, smoothing out the fluctuations before they could develop. Dark matter changed this. Because dark matter does not interact with radiation, it was not subject to radiation pressure. While the ordinary matter was being held smooth by its coupling to the photon bath, dark matter was already beginning to clump quietly, invisibly, building the gravitational scaffolding into which ordinary matter would later fall. When the universe cooled enough for electrons to combine with protons and the radiation to decouple from matter about 380,000 years after the Big Bang, ordinary matter was suddenly free to follow. Gravity. And gravity, by that point, was already structured. The dark matter had spent 380,000 years assembling into a web of overdense filaments and underdense voids, and as the ordinary matter was released, it fell into the dark matter's gravitational wells, flowing along the filaments toward the densest nodes, draining out of the voids, assembling into the first galaxies at the intersections of the web. The cosmic web is dark matter's skeleton made visible by the ordinary matter that fell into it. The galaxies are not the structure, they are the light that marks where the structure is. The voids are as remarkable as the filaments. They make up the majority of the universe's volume, vast, nearly empty regions where the expansion of space proceeds essentially unimpeded by gravity, stretching and growing as the cosmic web continues to evolve. They are not completely empty. Even the deepest voids contain a few stray galaxies, tendrils of very faint filament, a diffuse haze of warm gas, but their emptiness is striking enough that the handful of galaxies within them are sometimes called void galaxies. In a void, a galaxy evolves largely in isolation, without the mergers and interactions that drive star formation in denser regions. The void is not nothing. It is a different kind of something, a region defined by what is absent from it. The cosmic web is still evolving. Dark matter continues to flow along the filaments toward the nodes, feeding the growth of galaxy clusters. Ordinary matter follows, gas cooling and condensing into new stars in the galaxies at the intersection points. But dark energy is working against this process, stretching the space between the filaments, slowing the flow of matter, gradually reducing the rate at which new structure forms. At some point in the future, not soon on any human timescale, but inevitable on cosmic ones, the accelerating expansion will win. The filaments will thin, the flow of matter will slow to a trickle, and the cosmic web will freeze in place, its growth arrested by the relentless push of dark energy. What we see now may be close to the most elaborate version of it that will ever exist. The ship moves through the dark water under the cosmic web's faint imprint in the sky above. The galaxies at the intersections of invisible filaments, the halos of dark matter wrapped around each one. In the final passage, we return to the question of what it means to live in a universe mostly made of things we cannot see, and why the mystery, rather than being a failure of understanding, might be the most honest thing science has ever admitted. The ship has been moving all night, cutting its straight and steady line through water that reflects a sky full of things we cannot name. The galaxies overhead are embedded in halos of something that has no color, no charge, no electromagnetic presence of any kind, something that has been there since before the first stars formed, that built the scaffolding into which every galaxy fell, that holds the cosmic web together while dark energy slowly pulls it apart. We have measured it, mapped it, inferred its density and distribution across the observable universe with extraordinary precision. We do not know what it is. After nearly a century of observation and decades of direct search, the most abundant form of matter in the universe remains unknown. This is not a failure of science. It is science doing exactly what science is supposed to do, finding the edge of what is known and describing it honestly. The history of physics is a history of discovering that the universe is stranger than it looks. It looks solid. It is mostly empty space. It looks still. Everything is in motion. It looks intuitive at ordinary scales, at the very small and the very fast. It behaves in ways that have no analogue in everyday experience. Dark matter is the latest in this sequence of revelations, the discovery that the matter we see, the matter we are made of, the matter that has occupied the center of every physical theory since the ancient Greeks, is a small and perhaps unrepresentative sample of what actually exists. We are made of the exception, not the rule. The universe is mostly something else, and we do not yet know what that something else is. There is a particular kind of vertigo that comes with this realization, and also a particular kind of wonder. The 5% the ordinary matter, the atoms, the stars, the planets, the oceans, the living things feels thin when set against the 95% that remains unaccounted for. But that 5% has produced something remarkable, a creature on a small planet around an ordinary star, capable of looking up at the night sky and realizing that most of what is up there is invisible, of developing mathematics subtle enough to measure the invisible's gravitational effects, of building instruments sensitive enough to search for its direct signature. The 5% has become self-aware. It has looked at the universe and found it larger and stranger than expected. That finding is not diminishing. It is one of the most extraordinary things that has ever happened in the 4 billion years of life on Earth. The unknown is not a gap in the map waiting to be filled, it is the map. Dark matter and dark energy are not placeholders for real explanations that will eventually replace them. They are real explanations, the best ones we have for phenomena that are real and well measured and not going away. What they lack is a deeper account of their nature, a story of what they are made of and how they came to be, a connection to the rest of physics that would allow them to be understood rather than merely described. That story may come. The experiments are still running. The telescopes are still gathering light. A detection in a deep underground laboratory, an anomaly in a galaxy survey, a theoretical insight connecting two previously unrelated ideas, any of these could change everything. The door is open. And on the nights when the door is not yet open, on nights like this one, moving slowly through dark water under a sky full of invisible mass and accelerating expansion, there is something to be said for sitting with the mystery. Not as a defeat, not as an embarrassment, but as an accurate description of where we are. The universe is mostly unknown. It has always been mostly unknown. The brief interval in which humans have been asking questions about it is an eye blink against the 13.8 billion years it has been here, and the answers we have found in that eye blink are extraordinary. But they are not the end. They are the beginning of understanding how much there is left to find. The ship moves on through the dark, and the galaxies turn in their invisible halos, and the cosmic web stretches across the sky in filaments of light and shadow that no eye can follow to their end. The lanterns on either side of the deck cast their small warm gold across the planks, and the ocean ahead is dark and still and deep, and the universe above is mostly invisible and mostly unknown and completely, inexhaustibly there. You do not need to understand it tonight. You do not need to understand it at all. It will be there when you wake. It has always been there. And you, at last, can rest. Good night.